Okay, welcome back again to WSHS Algebra 1 Virtual Tutor. What we're doing today is we're going to continue factoring polynomials and quadratics, but this time they're going to look a little different again. So we have several different ways that we can factor based on the way the actual polynomial looks. Okay, so today's is going to be called a difference of squares. So we're going to factor again, but this time we're going to factor what's known as a difference of squares. And the difference, the word difference, in math also means subtraction, right? So this time what we're going to see today is a minus sign, definitely, and squares comes from like the term perfect squares. Okay, so you might remember perfect squares by anytime you multiply a number by itself, it creates a perfect square. Or anytime you take a number to the second power or you square it, it becomes a perfect square. So what a good idea is to remember or memorize or start to recognize what your perfect squares are, because when you see a perfect square, then typically that is a good indicator of having a difference of squares situation. Okay, so 1 squared, we're going to start with 1 and we'll go through 12. 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36. 7 squared is 49, 64 for 8, 81 for 9, 100 for 10, 121, and 144. I'm going to go ahead and add in 13 squared as well. 13 squared is 169. So it's a good idea to start remembering these and memorizing them by heart, because that'll help you figure out how to factor something as well. So after we find the perfect square, if I took the square root of that number, I'm just going to end up with my original, right? So the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Square root of 16 is 4. And you can continue that pattern there. So when I take the square root of that number, I'm just going back to the original here. Okay, so make sure you have that filled out in your notes there. So a difference of squares. What does that mean? So again, like I said before, difference means that there is a minus sign. You're going to see a minus sign. Difference, you could also think and remember things like different signs. So you would have, when you're factoring, you're going to have one positive, one negative. So difference, meaning I'm going to see a minus sign, and when I do the factoring, I'm actually going to have one positive and one negative in my factoring. Okay, and then squares, we're going to see some of these perfect squares here. We're going to see numbers like 25, or we'll see numbers like 4, we'll see 16, we'll see all these numbers that we just did our square terms or our exponents here, like 1625, 36, 144. You have to recognize these because these are our perfect squares, and it's going to help us figure out how to factor these. Okay, let's go ahead and dive right in with example 1. So anytime, again, I'm going to keep saying this, anytime I see the word factor in my directions, if it says factor, write the factored form, what is the factors, or what are factors, which one is a factor, that word factor should always pop up in your head, and you should always think, can I remove a GCF? Is there a greatest common factor that I can remove first? Okay, so let's look at example 1. I look at my coefficients here. I have 25 and 144. Well, 25 is 1 times 25, 5 times 5. That's it. And there is none, or I'm sorry, there is no number here that can be divisible by 144. Okay, or 144 cannot be divided by any one of those numbers there. So that means there is no GCF. Okay, but I noticed that 25 is a perfect square, right? 25 is a perfect square because that is 5 and 5. I also notice that 144 is a perfect square, if you remembered here. 144 is the same thing as 12 times 12, right? 12 squared, or 12 times 12, is 144. So a little checklist that we want to refer to is here. We want to remove any GCF. And then I see here, because I couldn't take out a factor, how else would I factor this? So do I have two terms? And yes, I do. I have two terms here. Is the first term a perfect square? And yes, we said that here 25 is a perfect square because that is 5 times 5. Is the second term a perfect square? And yes, it is. The second term was 144, and that is 12 times 12. And is there a subtraction sign? This is where the word difference comes from. Okay, is there a subtraction sign? Yes, there is. So when we can go through and I can check the boxes off of everything, if everything works out, then we have what's called a difference of squares situation. And we factor that a special way. So it's not like before where we had three terms and we had like a magic pair, what multiply to the last and add to the middle. Because here there is no middle term here, right? We only have two, not three. So there is no middle term here. So after you're going through these checklists and you see that all of these check, then we're going to do the difference of squares factoring. And how we do that is the first term here, 25x squared, we would write two sets of parentheses, and the 25x squared gets split in the front, right? So 25 is 5 times 5. That was our perfect square there. And we still have to split the x squared, right, into x times x. So 25x squared gets factored into 5x and 5x, and that goes in the front. And then 144 we said was 12 times 12. So we're going to split this up and put it on the back ends of our parentheses. 12 and 12. And then my signs are actually not going to both be positive. They're going to be, because there was a subtraction sign, technically this is a negative 144, or we can consider it being different or different signs. One is going to have to be positive and one is going to have to be negative. Now, it doesn't matter which order you put it in as long as you have one positive and one negative. So, and we go back and we can check this. Negative 144 is positive 12 times negative 12. So that does work out. If you had both of them negative, then negative 12 times negative 12 is a positive 144. So that would have made your sign right here positive or plus 144. So that's not going to work. Same thing if they were both positive, that would have made this a plus 144 as well. So you want to make sure that when you're factoring these, you also always have different signs, one positive, one negative. And this would actually be your answer. That's it. That's all you do for these. Let's try another one. Example 2, 16n squared minus 36m to the fourth. Now, be careful with this one because it's clear that 16 is 4 times 4, 36 is 6 times 6. So you might want to automatically go and do the difference of squares and kind of split it up right away. But remember that the first step, step 0 if you want to call it, is to always, always, always check for a GCF first. And this one is one of those examples where we do have a GCF, because if you look at 16 and 36, they are actually even numbers, so we can definitely at least take a 2 out and remove a 2, but there might be a higher one. So if I break down 16, 16 is 1 times 16, 2 times 8, 4 times 4. Would any of these numbers also work as a denominator or a divisor of 36? So can you do 36 divided by 16, get a whole number? No. Can you do 36 divided by 8? Not quite. Can you do 36 divided by 4? Yes, you can. 36 divided by 4 is 9. So because this has a GCF, I want to make sure I remove the GCF first. So I'm going to have to take out a 4. And when I take out the 4, what will be left in parentheses? So again, we're going back and we're going to have to divide each term by the GCF that we just removed. And so 16 divided by 4 is 4. So this becomes 4n squared. And negative 36 divided by 4 is negative 9. And I still have that m to the 4th power left, so that stays in there. So now I want to go ahead and verify, can I do anything else with this part in here? Can I factor that? Is there anything else that can be split up? And I still have two terms, right? I have a minus sign between those two terms. And I do see that 4 is a perfect square because 4 can be broken down into 2 times 2. And 9 is a perfect square because 9 can be broken down into 3 times 3. But what about the variables? N squared, just like x squared, we've been used to taking the variables and splitting those up into x and x, or in this case, n squared would be split up into n times n. But what can m to the 4th power be split up into? Anytime you have an even exponent, I don't care what the exponent is, as long as it's even, an even exponent is actually a perfect square. So the way we split an even exponent is just in half. So m to the 4th power can be split up into m squared and m squared, right? Because m squared times m squared is m to the 4th. If I had an even exponent, if I had m to the 10th power, how would I split m to the 10th power up? Well, that would be m to the 5th and m to the 5th. So anytime you see an even exponent, that is technically also considered a perfect square. So that can work. So back to my example here. I can do a difference of squares with 4n squared minus 9m to the 4th. I can split that up. So I would split this into two sets of parentheses. My 4n squared would be split into 2n times 2n. And my 9m to the 4th can be split up into 3m squared to the 2nd power, right? Times 3m squared. Because the 4 is just split up into 2 and 2. You can't forget you have to bring your signs, right? So this is a difference of squares, so we should have different signs, 1 plus, 1 minus. And always verify a positive 3 and a negative 3 gives you a negative 9, so that does work out. And last step, we can't forget that we had that GCF of 4 that we removed, so we just have to go ahead and bring it down, make sure it's included in our final answer. So there you go. All right, so last we have example 3. Example 3 here, we have 50x squared minus 2. Again, I see that this is not a trinomial. There is no first, middle, last term. So how would I factor this? Well, do I have a GCF, right? We always have to check for a GCF. Can we take out a greatest common factor? And we can, because between 50 and 2, 50 can be divided by 2 in order to reduce this, right? I can do 50 divided by 2, and that would be 25. So I can actually take out the GCF of 2, and when I remove that, what would be left inside of my parentheses? So to do that, we would take each term and divide it by the GCF. So 50 divided by 2 is 25, so this would leave 25x squared, and negative 2 divided by 2 is negative 1. So before I finalize my answer, I just want to make sure, can I do anything else inside of here? There's only two terms. I see the minus sign, so I want to check for a difference of squares. Are these two numbers, is 25 and 1, are they both perfect squares? Well, 25 can be broken down, right? It is a perfect square, and it can be broken down into 5 and 5. So this 25x squared can actually get split into 5x and 5x. 25x squared is 5x times 5x. 1 is also a perfect square. Sometimes people forget that 1 is a perfect square because 1 can be broken down into 1 times 1. And finally, we want to make sure we include our signs. Because this was minus, technically this counts as a negative 1, so we should have different signs. 1 positive, 1 negative. And we have to bring down our GCF of 2 and make sure we don't forget that. So this would be my answer. Okay, couple more. I thought we had that one as our last one, but we actually have 2 more. And I'm glad we have this example 4 here for a reason. I see that I have this 4a squared plus 9. So the question would say something like, write the factored form, or which is a factor of 4a squared plus 9. So I notice there are 2 terms. The first term is a perfect square. The second term, 9, is a perfect square. So 4 can be broken down into 2 and 2. 9 can be broken down into 3 and 3, right? There is no GCF that can come out, but that's okay. So sometimes you want to go ahead and say, all right, this is a perfect square, so I'm going to break this down into 2a and 2a and then 3 and 3. However, this part here, this plus sign, that plus sign should be a bell ringer. In order for it to be a difference of squares, we have to have a difference, meaning a minus sign. So that fourth check mark or that box will not be checked. So we actually cannot do anything here. So this is not factorable. The only way we'd be able to work it out is if this were a minus sign, okay? So there's nothing you can do there. And then the last one here, we have r to the fourth minus 121. So again, we're going to be factoring this, so we want to check for a GCF. And there is no GCF. So if I look here, though, the r to the fourth, technically that is a 1r to the fourth power, right? And we said again that any even exponent is considered a perfect square because it can be split, right? So r to the fourth can be split into r squared and r squared. R squared times r squared. So anything times itself would result in a perfect square here. So 1r to the fourth is a perfect square. 1 is a perfect square, and also 121 is a perfect square. And I do have that minus sign. So because I have the minus sign and I have 2 terms, both terms are perfect squares, that checks off all my boxes. So I can split this up into 2 sets of parentheses. The 1r to the fourth gets split into 1r squared and 1r squared, or just r squared and r squared. The 121 is actually 11 times 11. That's why I say you want to make sure you recognize those perfect squares right away. 11 times 11. And then the minus sign would indicate that we have different signs here. 1 positive, 1 negative. It's positive 11 times negative 11 is negative 121. So there's my answer. And that is it for difference of squares.